It'll make that noise when I'm going to record again. But I'll try and record when I go over answers to complicated calculations, because then you can watch them again as well. So I'm going to go through C, because you seem to be getting there now, but there's definitely not a lot of confidence about how to do it, because there's been some puzzled looking faces. So, with everybody okay with the fact that I've got 3 isotopes, 25, 24, and 26, yeah? And I know I've got 10% of this one, and then I'll call these ones X and Y. And so that must mean that because my total abundance is going to be 100, that X plus Y is going to be 90%. And that means I can say that Y is 90 minus X. Is everybody okay with that? Yeah? And so then we could just write our expression like before. So we'd have 24 times 10 plus, I'm going to have just done that wrong, 25 times 10 I should have written. Let's make that right. So 25 times 10 plus 24x plus 26, 90 minus x divided by 100 is going to equal 24.3. Is everybody okay with that? So then I can write 250 plus 24x minus 26x plus, and that's where I'm going to have to use my calculator because I can't remember what the answer to that bit is. 26 times 90, 2340. Is equal to 2430. Because I've timed that side by 100. Is everybody okay with that sentence? And so now I've got 24 minus 26, so I've got minus 2x, and then I just have to bring all the numbers over to the right. So I've got 2430, and I'm going to have to take away 2340 and 250, which gives me minus 160, which means that x is 80. And if x is 80 and y is 90 minus x, then y is 10. And so here I should have 80 and 10. Has anybody got any questions about that one? Can you see that they try not to make it too easy? Actually, when we had the last one that we'd done in class, we had to just do 100 minus x. So now they're already giving us one, so we have to remember to take that off, making it 90 minus x. So just be careful, because they kind of have been gradually making them harder. I think this is probably the hardest that they would do. And once you know how to do it, it's not so bad. But if you don't know how to do it, it's really, really tricky. So this next one is also pretty tricky. These are my least favourite calculations. Maths isn't my favourite, but they've got the door open in the maths office, so I can't even criticise maths. They can hear me all the time. So I find these quite tricky. So I'm not a confident mathematician, but I'm not a terrible mathematician either. But they make, if I was doing an exam, these would be the questions I would feel anxious about. Whereas the organic chemistry ones, I'm like, oh, you just make those up. Here I'm like, oh, I've actually got to think carefully. And the bit, I'm going to get rid of that. The bit that you really have to know that is not particularly obvious from anything in the question itself is how to work out the mass of an ion. That's the first step. So if you read through it, they've given us the kinetic energy. Yeah, so we've got that. And they've given us the time of flight here. So we've got that. And we want to find that. Yeah?
For the Avogadro is constant, is it meant to be grams per mole? Or is it just per mole? You said like
Yeah, it's not in grams per mole because the Avogadro is constant is just a number. So it means I've got that many per mole.
okay.
So just like saying I've got 12 eggs per dozen, it's a number, it doesn't have a unit as such. Yeah? So this is just telling me I would have that many of them for every mole. But for some reason, that's ended up as a little plus where it should be times. Yeah, don't know what happened there. So the problem I appear to have at the moment is that I need to be able to find V in order to find D, but I appear to have two unknowns, V and M. Yeah? And I'm pretty much stuck because I've got two unknowns. But I can actually always work out M. As long as I know the mass of the isotope here. So can you see it says 25? So the 25 mg plus is going to be essential to me finding the mass of one ion. What I want to know is the mass of one of these ions. So what's important is that I remember that if I've got a mass of 1 mole of anything, then that will be equal to its relative mass in grams. So are you okay that if I have 1 mole of this, then that would weigh 25 grams? Is everybody okay with that as a statement or not? That's something that you do at GCSE. So if I have 12 grams of carbon atoms, I'd have 1 mole of carbon. If I had 16 grams of methane molecules, I'd have 1 mole of methane. Yeah? If I had 2 grams of hydrogen molecules, I'd have 1 mole of hydrogen. So as long as I know what the relative mass of my substance is, then I actually know how much 1 whole mole of that substance would weigh. Is everybody okay with that? What's really annoying is that they want us to weigh our 1 ion, not in grams, but in kilograms. Really annoying, and usually this is what causes people to make a mistake and get the final answer wrong. So this is actually going to be 25 times 10 to the minus 3 kilograms. I've just divided that by 1,000. I could say 25 over 1,000 kilograms, but I don't have to put the dividing line in if I do it times 10 to the minus 3. So is that statement okay? So also, 1 mole of a substance has Avogadro's number of particles in it. So I can also say that 1 mole of 25 mg is 6.022 times 10 to the 23 ions, and we'll put the plus back in. So if I know how many ions I've got, and I know what the total mass of all those ions is, then I can work out the mass of 1. Yeah? So now I can say 1 of these ions will have a mass of 25 times 10 to the minus 3 kilograms divided by 6.022 times 10 to the 23. Sometimes in these exam questions they will break this up, and so this would be a question on its own, and then you would have to take that answer forward to work out the next part.
Yeah. So is this technique just only used for ions?
You could use it for anything. So I could work out what 1 molecule weighed. If I know what the total mass of 1 mole is, this is always going to be the number of particles I've got in a mole. So if I knew that the average mass of a sample was 85, then I knew that they were molecules, then I could work out the mass of 1 molecule by dividing that by 6.022 times 10 to the 23. Yeah. So that's just the number of particles, but it doesn't have to be an ion or an atom or a mole. Just like I can have a dozen eggs, a dozen hippopotamuses, a dozen pencils. The size of the item doesn't matter. It's just telling me the number of items that I've got. Yeah, it's just a horrible number rather than 12 for a dozen, which is a nice number that we can kind of picture and hold in our head. This is a horrific number that we cannot picture and hold in our head. I can't even begin to imagine something that huge. I can barely even write that number of zeros, let alone conceive of what it would actually look like, which I think is what makes it harder. There's no harder a concept than a dozen, which we've been able to understand since we were tiny. But because the number is so horrible, it makes it seem like a much harder concept. But actually, it's just telling us that I've got a dozen, a fixed number, but it's a horrible number, that's all. Yeah? So are you okay that we can actually find M? It might not have been obvious at first, but we can find M. So once we've got M here, can you see we can find V? Because if I've got KE and I've got M, I can rearrange this expression to find V. I'm going to do it slightly slowly. Let's change colour. So I had KE equals half MV squared. So if I double both sides to get rid of the half, I can say 2KE is MV squared. And then if I divide both sides by M, I'll get 2KE over M is V squared. And now I square root both sides. So I've got root 2KE over M is equal to V. So I can now find V. You could learn that. Personally, I would just work it out. I'm not very good at learning things. And I made that look hard. But for me, I would rather just rearrange it and learn it in one particular format and rearrange it as I need to. But some people are less confident with rearranging. And now that I know V, once I've done that, I can substitute that in, because I want D, and D is V times T. So can you see I'm just going to then have to times that by T. And then try to think about what you're expecting D to be like in terms of numbers. So distance is the distance of the flight tube, how far my iron's going to travel. And we're usually looking at, well, the unit is meters, and my flight tube isn't going to be more than 3 meters long. It's just not going to happen. If you end up with an answer like 85, think about it. Are you really going to have a flight tube that's nearly 1 kilometre long? Well, it's not like that, but you know what I mean. It's going to be ridiculous. Where am I going to put it? It's going to be far too big. So I have to think about my numbers. I'm expecting numbers usually for the flight tube of between 1 and 3. Okay? And that can help you to spot if you've made a mistake. When I do things on the calculator, I'm an enormous lover of brackets. I do brackets everywhere. Make sure that you are happy and confident with your calculator. And don't try and do calculations on someone else's unless they're exactly the same as yours, because their button pressing order might not be the same as yours. Because these two probably work in slightly different ways. No, maybe not. You guys have got a stamp one. Nobody's got one of those ones with a big graph thing on it. Then they have a different order of button pressing, and I can't work them, so just never ask me. I can work these are fine. But the other ones, you have to press the buttons in a different order. So just make sure you know how to work your calculator.
What did you say the approximate distance should be?
I'd say between 1 and 3. That usually seems to be the answer. But remember, you're not going to have an enormous distance that it's going to travel along the flight tube, because the mass spec machine's got to live in a building, and so it would have to be a very, very big building if it was going to hold a very, very long flight tube. But it's also not going to be really short, because we want to get separation between our ions. That's how we're going to be able to tell. They're going to need time, that distance to separate out. So when you're trying to write your answer, you should go for the lowest number of significant figures in the question or in the data that you use. So we didn't use any of that. They've given us 3 here, 3 here. That one's got more, so 3 it is. Yeah. If you've rounded your numbers, you might find that some of you have got an ever so slightly different answer to the other. When I do it, I tend to keep all the numbers in my calculator, and I don't round at all until the end. But that might cause some of you to get ever so slightly different answers. If you don't round at all, you should have got 2.12. Yeah? If you've rounded somewhere, you might have got a slightly different answer. They will sometimes give you a range that your answer can fall between because they take into account reasonably rounded. Yeah? You okay? Yeah. You okay? Do you manage to go to work? Yeah. It's the whole how to put the numbers in the calculator. It sounds a bit patronising, but it's actually a little bit of a challenge. And if you press the wrong button in the wrong place, you can end up with a very, very different looking answer. So that's why it's worth kind of thinking about what you're expecting the scale of your numbers to be, so that you're not just blindly copying. We trust our calculators so much. So this must be right. Because you can't do these things in your head most of the time, can you? So the calculator is our guru, but it means we can become a bit too trusting. So you have to make sure that you're thinking as well as using the calculator. Okay, have a go at the next one. Alright, they're quite different, some of these, and I know you might find some of them hard. I might just stop this one again because it's a bit boring if anyone ever wants to watch it. And I can just split them up into